So 5.3, the concentration changes over time. This is a learning objective that has lots of math in it. If you look at the essential knowledge, you're going to see a decent amount of formulas. Many of those formulas are on the formula sheet that you will get on the AP chemistry exam. So have that formula sheet handy, because we will refer to it from time to time. So if you remember from the video a few days ago, we talked about how the rate of the reaction changes over time. Because there's less reactants, the rate will slow down. So then if we are going to predict how much product is left after 2 days or 20 minutes, we have to take into account the fact that the rate is going to change over time. And we said that was really calculus. So there's a lot of really interesting derivations that go along with how we get these formulas that we don't need to go into in AP chemistry. Basically, the formulas are given. The formulas will be different depending on whether it's first order or second order, and even zeroth order. Zeroth order means the reaction rate doesn't depend on concentration of reactants at all. It's rare, but every once in a while they throw one of those in. So we'll take a look at that. But we're going to spend this video really looking on first order reactions. They're the most common. So these are the formulas that we've used so far for rate. And rate is the change in one of the chemicals. And in this case, we would say A, one of the reactants. So negative change in delta A over delta T. And then rate equals K times the concentration of A to the first power, because we're just dealing with first order reactions for this first video. Hocus pocus calculus, and we get these fancy formulas that have T in it, that have time in it. Yes, that is ln as a natural log. ln, so the natural log of the concentration of A at time T. So that's 20 seconds down the road, a minute down the road, whatever. Minus ln concentration of A at time 0, meaning the original concentration, equals negative KT. We can rearrange that formula into a few different forms, and they're going to be useful depending on what the question is asking us to solve for. If the question is asking us to solve for, let's say, time, how long will it take? I would use maybe that formula or this formula, because time is on just one side. Remember, subtracting logs, like dividing them. And this one I would use especially if it was asking for what is the concentration after 10 minutes or 30 minutes, something like that. So we will just choose whatever version makes most sense depending on what the question is asking us. So we will all these problems are either going to be asking us to find the concentration after a certain time, or the time it takes to get to a certain amount. So let's just do a whole bunch of these sample problems here. Make sure you have a calculator handy. So the first question says first order rate constant for the decomposition of a certain insecticide in water was 1.45 inverse years, negative years. A quantity of this insecticide is washed into the lake on June 1st, leading to a concentration of 5.0 times 10 to the negative 7 grams per centimeter cubed of water. So this is my concentration at time 0, right? That's my initial concentration. Assume the effective temperature is 12 degrees Celsius. What is the concentration of the insecticide of the following year? So the question is asking us, what's the concentration, an amount of time down the road? And so I would use this version of that equation just to make the algebra easier. Negative KT plus ln, the concentration of A at time 0. Plug in the values. The negative 1.45 inverse years times the time, which is 1 year, plus ln, the concentration of A at time 0 was 5.0 times 10 to the negative 7 grams per centimeter cubed. Look at what happens to my units here, right? The years units cancel out, which makes sense. Now I actually have to plug this into my calculator, and what I will get is ln concentration of A at time t equals negative 15.95. And this is, remember, ln is really log base e. And so we're going to take this from log form and put it into exponent form. And so that's going to be e to the negative 15.95 equals concentration of A at time t, right? Log base E. So e to the negative 15.95 equals the concentration of A at time t. And you just plug that into your calculator, 1.17 times 10 to the negative 7 grams per centimeter cubed. Pretty straightforward, even though it looks very scary. B, now this one's asking how long will it take? So I'm going to use another version of this formula. How long will it take for the concentration of the insecticide to drop to 3 times 10 to the negative 7 grams per centimeter cubed? So in this case, I'm going to use ln concentration of A at time t over the concentration of A at time 0 equals negative kt. So that would be ln of 3.0 times 10 to the negative 7 over 5.0 times 10 to the negative 7. The units, grams per centimeter cubed, would cancel out, equals negative 1.45 inverse years times t, right? I divide, take the natural log, then divide by negative 1.45 inverse years, and I get my time equaling 0.35 years, right? That'd be about 4.2 months. So this is actually, kind of useful formulas here. Okay, we have 2 more practice exercises here, and this may be a good idea if you want to pause, try these problems on your own, and then check your work. At 25 degrees Celsius, the decomposition of dinitrogen pentoxide to N2O and O2 follows first order kinetics. So that tells you what formulas to use. Gives us the K. Assume the sample with initial pressure of 760 torr. So now when we're talking about gases, we could use molarity as a unit of concentration or unit of amount, but pressure also works. So we will often, for gases, use pressure as kind of a stand-in for concentration. If it is initially 760, it decomposes to 650. How much time has elapsed? So I'm going to use that second formula, right? The natural log of the new concentration over the starting concentration equals negative KT, right? The K we know is 3.4 times 10 to the negative 5 inverse seconds times T. Solve for T. T equals 4.598 seconds, or answer choice C. And then the next one, the decomposition of dimethyl ether, again, it tells us that it's first order, tells us the rate constant. If the initial pressure is 135 torr, what is the partial pressure after 1,420 seconds? So I'm going to use this formula, ln concentration of A at time t, because I want to know what is the partial pressure after a certain amount of time. Negative KT plus ln concentration of A at time 0. Negative 6.8 times 10 to the negative 4 inverse seconds times the time, which is 1420 seconds, plus ln, we'll just use 135. When I find that, I get 3.9 torr. Right, torr, I should have mentioned this in the previous one, is another unit of pressure. Torr is equal to a millimeter of mercury. And then we can look at what this will look like graphically, because this is a very common multiple choice question. If I look at this version of the formula, I can notice that it looks suspiciously like the formula for the equation of a line. If I were to graph on the y-axis the natural log of the pressure, and on the x-axis I were to graph time, then what I would notice is that this actually turns into a straight line, whereas the y-intercept is the initial concentration, and the slope would be the negative of the negative of the rate constant. So oftentimes the question that will be asked will be, is this reaction first order? And you can tell if a reaction is first order from the graph. If you graph the natural log of the pressure versus time, if that turns out to be a straight line, it must have been first order. Second order and zeroth order will not be a straight line when you graph the natural log. So you can't necessarily tell it by looking at the graph of just the pressure versus time, but you would take the natural log of the pressure. So that's first order. Second order is very similar. It's just a different set of formulas.